Yeah, dear delegates, a very good morning to one and all. On behalf of the Department of Computer Science and Engineering, SRM Institute of Science and Technology, I welcome you all to the fifth day of short-term training program on big data, machine learning, and deep learning. We hope that all the sessions held so far was very informative and useful. For today, we will be having two sessions. The first session will be on recurrent neural networks, deep learning, and research avenues in AI. The session is supposed to be presented by Dr. Meenakshi Sood, but due to emergency reasons, she is not able to join us. So this session will be deliberated by Dr. Lata Parthiban, who is currently the professor and head in charge of the Department of Computer Science, Pondicherry University Community College. Dr. Lada Parthiban holds BD degree from Madras University. She is a dual PG holder with MS in Software Systems from BITS Bilani and ME in Computer Science and Engineering from Anna University. She completed her PhD from Pondicherry University. Dr. Lata Parthiban has 26 years of teaching experience, which includes 8 years at Pondicherry University Community College. She has published around 109 peer-reviewed Scopus and SEI indexed journals. She has presented more than 60 papers in various conferences and is an invited speaker in many conferences. She has received Best Paper Awards in IEEE conferences in the year 2009 and 2013. She is the reviewer of many papers in many international journals like IEEE, Elsewhere, and Springer. She is the editor-in-chief of International Journal of Human-Machine Interface of Artificial Intelligence Association of India. She is a member of professional societies like IEEE, CSI, IACSIT, IAE, ISTE. She has reviewed sponsored project proposal for SESH Foundation, which is one of the leading scientific organizations in the world. So far, she has guided around 18 PhD scholars. She has 3 research projects to her credit sponsored by CSI, NVDIA, and MHRD. Now, Dr. Lata Parthiban will be enlightening us about the recurrent neural networks, deep learning, and research avenues in AI. Now, I hand over the session to Dr. Lata Parthiban. Over to you, madam.
Thank you, ma'am.
Ma'am, thank you once again for accepting our invitation on such a short notice, ma'am.
Oh, fine. It is a pleasure, ma'am. So, good morning to all. Actually, ma'am, the participants are students or faculties, ma'am?
Ma'am, we have faculties and research scholars, ma'am.
Okay, fine.
Few students too.
Okay, fine. Okay, ma'am. Right. So, very good morning to all. It's a pleasure meeting you all today. Actually, all of us are aware that AI has, this field is growing every day, and more research are happening throughout the world. And most of the research scholars are doing research in this area only. And the topic that is given to me is recurrent neural networks. I hope that most of you would have gone through the other neural networks like backpropagation neural network, SVM, etc., etc. Now, what I thought was I will give a brief introduction about neural networks and start how recurrent neural networks differs from the normal neural networks. I'll just start my presentation. You are able to see the screen, ma'am?
No, ma'am, not yet. No.
Okay.
I think it's in the process of getting shared. No.
Okay.
Yes, ma'am. Now we are able to see.
You are able to see. Okay, fine. we know that neural network, we have inputs and we have outputs. In between, we have a black box, which we call it as a hidden layer. The basic intuition we can have is we can see it as a computational graph, where you have nodes and edges for transmitting the information from node to node. That is, from input to the output node, information is transmitted, and we are able to create so many models, etc. with this neural network. Coming to the basic neural network, which is the feed-forward neural network, you can consider it to be having so many nodes in the input layer, where each node represents one input, and you have output layer, where you may be having single output or multi-output, and you have, basically, we think about one hidden layer when it comes to the normal neural networks. See here, you have X input. This is the hidden layer we are representing. And we can very well see that you have, if you are having a neuron, it is capable of, when you consider a single computing unit like our human brain, it is capable of evaluating a single primitive function. We can very well see that we have a lot of problems. Sorry. A feed-forward neural network, you can consider it to be a simple neural network, a simple neuron having X input, Y. Then you have this G is called the activation function of this hidden layer. By this, we normally, the terminology used is black box, and F is the activation function of the output layer. The output layer can have many activation functions. Commonly used activation functions are a lot of linear functions, where we use it for modeling, that is for regression problems, and other software functions we use for classification problems. This we are all aware of. And the normal activation functions we use are sigmoid function. This is the sigmoid function we use. And we have this tan h function, hyperbolic tan h functions, where we have this this sort of graph. Actually, everywhere what we are able to see is lot of mathematical calculations are involved whenever we are using this neural network, because of the mainly because of the nonlinear nonlinear functions we are using. Because whenever we are trying to model a system, a lot of nonlinearity is involved, and we have to take care that whenever you are using activation function, weak signals we don't pay much attention. I mean, weak signals we have to slightly bring it back to the normal condition, and stronger signals we don't pay much attention. So these functions will be very helpful in real-time systems. Now, we know that whenever we are talking about neural network, we have this training and testing. Whatever neural network we are using, we have to train it, and then only we can validate the system by testing it with the known data. Now, real world problem, whenever we are using this neural network training, lot of parameters are involved in the model. And we have to choose the parameters what we require. And obviously, it is not single objective. We have multi-objective problems that are solved. And we requirement is high level of parallelism is required. And obviously, we try to minimize the errors. Whatever real-time function, real-time system we are modeling, we try to minimize the errors through some method. So error minimization problem is the main thing we will be concentrating whenever we are training the neural network. Whenever, only then testing accuracy will be higher, obviously. So this backpropagation algorithm, we have this gradient descent algorithm, which you would have already gone through in the previous sessions. What we try to do is, you have in the backpropagation algorithm, we have two phases. One is the forward propagation, where from one network to other it goes. That is, you from node to node there is a jump to the output. Here, whenever there is a error encountered, we do the back propagation in BP networks, and weight updation has to be done so that correct weights. We have to take care that we are basically mapping the input with the output. We have input for some system and we have output for some system, for the same system. So we try to map the input with the output in all the neural network. That is what basically the training is. So whatever calculations that are having that we are doing inside with weights, activation function, etc., we have to take care that the cost function does not, not at the cost of the mapping. That we have to take care. Like many limitations we find in the normal neural network is we have a fixed size vector as input, size vector as output, which is one of the major disadvantages. But for whenever you have an image, it is fine. We know that 0 to 255 is there, so there is no problem in that. So this input mapping, input-output mapping using fixed computational steps is going to be easier in normal neural network. But in real-time system where we use time series and all, this type of modeling will not work out. Normal other modeling we can easily work out because they are not time dependent. Time series problems was found to be very difficult to model with the normal neural network. So mainly when the input and output are real valued sequences, this modeling became very difficult, and so they went in for this recurrent neural network. So whenever we have time series, when we are supposed to model any time series, we have to go in for recurrent neural networks because normal neural network does not work here. This RNN proposed long back in 80s itself, because what they this time series is existing for a very long time. We know that the structure that was proposed initially was similar to the feed-forward neural network, with the main distinction that you have a recurrent hidden state. See here, H is the hidden state there. This recurrent hidden state, it is going from with each activation, it is moving from from previous state to the next state. So this will be dependent on the previous cycle. H1 will be dependent on H0. Similarly, H2 will be dependent on H1. So whenever activation happens, the modeling will happen. So here the main thing is, because of the time series, for each cycle, the activation of each time is dependent on the previous time. That we have to know. So this is the basic concept in which our recurrent neural network works. For time series only, for modeling the time series, this will be a very good option for us. See how this basic, all of you would have seen our basic neuron with activation functions, input, output, and what is happening inside with the sigmoid function, etc. Now, whenever we talk about simple neural network, see here, you have the input X, you have the output Y. We are putting, so it is time dependent. So XT and YT. Here we can very well see that HT, in the hidden layer, you have the sigma, and see here, this whenever we talk about HT, it is dependent on HT minus 1. So on the previous state, it depends on the previous state. So ht equal to sigma wxt plus q of ht minus 1. So main thing you have to keep in mind is, don't worry about all these formulas. The main thing we have to keep in mind is the function is dependent on the activation is dependent on the, this will become activated only when it has this. And we have a lot of control mechanisms that are available. Similarly, ht plus 1 will be dependent on ht. So this is a single unit we can have in a recurrent neural network. Time recurrence, we can very well see that the hidden layer activity ht is dependent on the past hidden layer activity. And similarly, the next hidden layer activity will be dependent on the present hidden layer activity. So here we can see the dependence on the previous hidden layer activity everywhere. So this is the only dependence we are having, and it is a time series. Actually, this dependence is always non-linear. Linear dependence we can easily model. Here, the dependence is considered to be non-linear. Okay. This is the main thing we have to, basic thing we have to know whenever we think about recurrent neural networks. Actually, here if you can see, whenever we unfold, when we have a recurrent neural network, whenever we unfold, the hidden layer increases, similar to our deep neural networks. Like when this was introduced long back, the idea that this is called deep neural, nothing was there. You know, they were just thinking. So there is a very good correlation we find with the deep neural network we are using on today. So we can see that normally we see hidden layer limited to 1 in all our neural networks, but here in recurrent neural networks, the present activity is dependent on the previous hidden layer. So now when we are talking about sequences in time, so actually you can call that, it is similar to our back propagation, slight modification we can say, back propagation through time, we call it as BPTT. So for each training, you know, you have maximum sequence 1 to n, and for each length of the sequence, we are trying to unfold the neural network into normal feed-forward neural network with k hidden layer, similar to our BP algorithm. You proceed on like that. Sorry. The main problem with BP through time is, you know, high cost, because we are having a single parameter update in that ht plus 1. We are updating it with the previous thing, no? So single parameter update, we cannot use it for long iterations. When we have long iterations, it becomes very difficult. And when we try to use RNN on sequences of length 100 cost, you know, obviously it needs 100 layers. So it becomes very difficult. So, you know, people are happy with our back propagation neural network for the previous application, except that whenever we have this time step, you know, there was problem. Now, how to deal with this? Many new techniques were researched, and many new techniques have come up. And you know, we have only every time step, you know, for T1, T2. If T2 is found to be lesser, then obviously it will be cheap. Parameter update, everything will be cheap. So trusted, you are truncating the back propagation by if T2 is small. So they were, you know, for reducing the number of layers, we were doing this. Now, Obviously, as I told, the cost was high because there was parameter dependence. Now, what to do properly? In a gradient back propagation phase, the main thing is, if weight matrix associated, like whenever this lambda 1, mod of lambda 1 is less than 1, weights are very small. You had this vanishing problem, and whenever weights are bigger, you have this exploding gradient problem encountered. In the exploding gradient problem, what they do is they clip the whichever gradient is becoming large, they clip it, truncate it. So that handling this was, when the weights were big, handling this was very easy. But whenever we have this vanishing gradient problem, we try to make this nonlinear dependency to linear dependency using this LSTM and GRU. We'll see what is this LSTM and GRU. LSTM is nothing but long short-term memory, where we try to have a memory cell which stores the state. Again, here the cost will be slightly more. It was first proposed by Hochreiter and Kimunder in the year 1997, and it has a lot of variants have come. But this LSTM architecture has been long standing for the recurrent neural network. You have this memory block which stores the state. Actually, we saw that the hidden layer, the present state is dependent on the previous state. So obviously, how to handle this is, you have a memory cell. You have a input gate which controls this memory cell, and you have a forget gate which controls what to forget. Whatever we are storing, we cannot have it permanently. So you have to reset it or forget it. If it is not regularly used, whatever we are putting in the memory cell, if it is not permanently used, if it is not going to be used often, then you set it to 0, reset it to 0, or have a control what to forget. So it is deleted. Basically, what is there in the memory cell will no longer be used, so you delete it. Output gate control the amount of content to be modified. So the main thing is this LSTM unit we are using, that is the long short-term memory unit, decides on whether to keep the existing memory through the gates. We have this input gate, output gate, forget gate. These three gates take care that what is the input, what are the things to be forgotten. If it is going to be there, then it is passed on to the output gate. If it is forgotten, then nothing will be passed on through the output gate. If it is not forgotten, whatever is stored in the memory cell will be passed on. So this is the main idea behind the LSTM. So this basic unit of this LSTM, you have this here, whatever we are storing, you have this X and Y. This is, let us think that this is H1. We take it here. This is HT plus 1. If you think that this, whatever is coming out here, stored in this memory is not required, then you can enable the forget gate and then carry on. So these are the main thing that is involved, that is the memory block, which is a LSTM unit. See here, CT plus 1, CT, previous state, and then next, whether it is to be carried out or not, it is decided here. If you are enabling the forget gate, obviously the previous state, whatever is there will be deleted. So whatever input we are having xi, with all the gradient and all those functions will be passed on to the next stage. This happens. So this is how the input gates, see here, the input gate controls the degree to which the new memory content is to be added to the memory cell. You have the input IT, what is to be added to the memory cell. See here, you have the previous CT minus 1, and so this will be the CT, whatever you are having. If you need it, you have, otherwise you disable it. Yeah, or we can say, see, you can imagine it to be a gate. That is what we know, the normal working of the gates. So here the idea is, if forget gate is enabled, then the gate is closed. If forget gate is disabled, correspondingly the content will be carried. It depends on whether to have the content of the previous state or not. We transfer it. Transfer FT correspondingly. Or if you are enabling the reset, obviously the memory content will be reset to 0. So the whatever is passed in the previous will not be passed, and whatever you wanted this memory to retain, you introduce or retain, whatever it is. See, the main use of this LSTM memory block is, there are times where we try to forget what is already there. Whenever we are writing something, or whenever we are with the internet, when we are writing some content, we see that spelling and all is helped. It, when we write a time or something like that, if I put TI, then the next 2 letters come in. So here we see that some help is coming. Actually, these are all the content that is stored already in the text corpus. We are already having a text corpus, which we are trying to help us with the words starting with those 2 letters. Whenever we change it, we see that next thing comes. So there are times when we write a paragraph or a file, we find that we are not going to retain the same thing. So there are times when we require that contents are deleted. So this we call it as fading states, where we delete the content or reset the memory block. Excuse me, 1 second. So LSTM memory block looks like this. You have the CT, you have CT minus 1. So here, whether you wanted to have the previous state, ID, so these are all the contents that is going to go out. So new memory content is added. This is the new memory content that is to be added, and it is stored, and it is transmitted to the next state. Fine. So this is the main memory cell we are introducing in LSTM, which is very, very important. It helps in storing the content, but obviously we can see is the cost of RNN will be higher because of the introduction of memory content. If you are having a larger amount of memory content, obviously the results will be good. There is no doubt about that. Whenever we are having memory content, the results will be good. But at the cost of calculation, everything will become high. You have a tan H function here. So this is how it looks like. So you have the CT minus 1 hidden layer. So whatever you are introducing coming in here, you have the output. So altogether, this is what is. Whenever we are having vanishing gradient problem, this can help. Similarly, the another technique that is used is gated recurrent unit. One is LSTM, and the next is gated recurrent unit. This was proposed by Cho et al. The main advantage here is you don't have any memory cell here. You just have the update gate and the reset gate. Whenever you wanted to put new content, you update the gate. Whenever you wanted to make it 0, you don't want anything to be there, you reset it. Sorry, here it is gate. I think it's put it as. So these are the, whenever here you don't have any memory element to store it. So obviously this GRU cost is much lesser. The model parameters involved here are input with the time t, weight matrices, W is nothing but a weight matrices at the two parts. Similarly, this is a Ri, all these are the activation, hyperbolic, every function, activation function. So here actually main thing you wanted to see here is Z3, this update gate, this determines how much unit update is required. If you don't want to, if there is a reset in this HT -1, it keeps only this. So this update gate takes care that, to how much extent you need to update. If your RT is closer to 0, that is the gate is off. Obviously, it is reading the first symbol. First, here you have the next, it is connected to the next one. Now, if this RT happens to be 0, obviously you can consider this gate itself to be off. So it goes to the next sequence will be the first symbol from the input sequence. So whatever is computed previously is forgotten. So this will be, cost of this will be very less. Similarly, update gate decides on the, as I told, update gate decides on whatever activation function is required. Sorry. This we have seen. Everywhere you can see there is no memory cell as we saw in the LSTM. Okay. So this gated recurrent unit became famous after this LSTM. The cost of LSTM was higher because of many layers that were introduced. Whenever we try to model something, what happens is we have to wait for a long time, which is obviously difficult for us to do. The calculation time will be much more, and because of the non-linearity, it becomes difficult. Now, this hidden state, here you have this HT 1 minus, we are introducing the activation at the time t, which is HT is dependent on the previous state, and you have the activation HT. So this is what it is. See, we can see all the components as in LSTM except the memory content. So this is one unit. It goes on like that. So these two, even though many techniques were introduced to improve the performance of RNN, this LSTM and GRU are mainly used because, they are much cost effective. So we will next go into why do we need this recurrent neural networks. 1 minute. Now, why do we need this recurrent neural networks? In fact, with a lot of layers, we can slowly imagine that it is similar to our convolution neural network. Why this sequence tasks are calculated, all these things we'll see now. And in this vanilla recurrent neural network, it was having forward bidirectional pass. This was, way back, this was introduced. This was the first one introduced when recurrent neural networks was found. And after this LSTM, GRU, today we are having all these things. See, we are basically seeing what problems, we have in classifications which can be easily solved by networks, by our recurrent neural network. Here we can see the similarity, this picture. You have a lot of pictures, and based on the distribution of classes, we identify whether it is a cat or panda. See, cat is 0.1 and panda is 0.9. So actually, how guessing is done? So sequentially, we have to study the image and then decide on what it is. So we have a lot of machine learning algorithms, and another important topic we can see is this language translation. A sentence written in one language converted to another language. Another example is, whatever we wanted to speak, simple speaking, we just say 2 or 3 words, and what we are having in mind, we are able to deliver. That, that also you call it a sequence learning. Whatever we are speaking sequentially should have, what comes next, it is dependent on the previous thing. So this is what you call it as sequence learning. In input images, you can we can see that width, length, color channels, and the distribution of classes, all these things are taken into account. And similarly in see, this is all sequence. You are saying something, sequence could be how you are able to correlate the input and the output sequence. Sequence labeling is another important problem to deal with, mainly with the feed-forward neural network. You have this autoregressive models, which was initially in existence, and predict this autoregressive model was the first model to predict the next term that comes in the sequence after a delay. This feed-forward network were later on used for this. It is a higher end of this autoregressive model. It can be used, and whenever we have dynamic models, we had this. See, whenever sequence labeling for dynamic systems became difficult, with a lot of hidden state in the system. How to deal with this dynamic labeling is only this RNN model. See here, we are updating the, see, this is the input and output, and this is the hidden layer. We are updating the hidden state in a deterministic way. That is, as I told, you had either you are having LSTM or GRU model. From this, you are moving one. From this, the information moves like this. This is H1 and this is H2, means H2 will have some content of this. H3 will have some content. It is going like that. It is moving from the initial to the next states like this, hidden state like this. So you have a chosen word where you are propagating in the network in a dynamic way. The main advantage of using this RNN are you have distributed hidden states. And you have memory element, means you can store a lot of information about the past efficiently. In other things, we don't have memory storage, which is a disadvantage. In nonlinear, you can continuously update. We saw the gates, input and output gates, which were continuously updating and helping us. So, this RNN is considered to be a powerful network whenever we have nonlinear dynamics, and the storage is also there. The first RNN that came into existence, you called as vanilla RNN. It is, you know, it started from this multi-layer perceptron with a single hidden layer only. We can very well see that, see this, in this hidden layer also, you know, like 4 techniques are available: one to many, many to one, similarly many to many, and one to one. I will discuss about that later. This hidden layer activations, you know, when it takes step by step, it will be very efficient. So see, in the forward pass, it goes like this. You have the hidden layer. These are all similar to our backpropagation neural network only. Similarly, in the backward pass also, you know, whenever we do the, why do we do the backpropagation is through time is, you know, like error is going to be reduced. Our idea is to reduce the error that happens. If you don't reduce the error, obviously the model we are creating will not be highly successful. So during the back propagation through time, you have to calculate it using these forms, and you know, like we have to calculate the weight of the hidden layer, all these things, derivatives. You would have studied these things. See here, uh, here you have a forward pass and a backward pass. So this is what, you know, this is t and t minus 1, and you can you know, hidden states, input and output, input and output. See here, forward it is moving, and you know, whenever error is there, you have a backward state propagation, so that error is going to be reduced. Simple forward pass means you have hidden layer which is just passing. Here you are passing it. Whenever you know, you have some threshold limit for the error. If it is going to be higher than specific threshold, then you, we wanted the error to reduce, you back propagate it, and you backwards comes here, changes the thing correspondingly, and your error gets reduced. 1 minute. So this is about forward pass, backward pass, similarly training. See, whenever most of us see this neural network book now, we have plenty of books coming in, and whenever we see these mathematical thing, you know, we get diverted sometimes. You know, if we are able to understand the concept, it is very easy to deal with these problems. And this is the bidirectional pass algorithm. Forward pass, you know, pass forwardly in a, you know, forward passing like this. So from this is ht means ht plus 1, ht plus 2, like that it goes on. After you know, near in the end, you just back propagate it. So similar to our back propagation neural network, except that you have time dependent data here. As far as this recurrent neural network is concerned, you know, like um, many, like it is used in a lot of engineering applications, and obviously it is a gradient descent based algorithm like our back propagation neural network, except that it is time dependent. And as I told, you have this vanishing and exploding gradient problems, which will be taken care. In exploding gradient problem, you have a threshold and cut the remaining things, whereas the other one you go in for reducing the thing with using this LSTM and GRU. And this is the same thing. Just I thought, you know, here a comparison taken from a book where a comparison of this vanishing gradient problem. See here, why we call it as vanishing is this is the gradient information. See here, slowly this is reducing. Somewhere we would have removed the content of this. Here this content is vanished here. Whereas you see that you have the gradient information present saved here. See here, you get the output here. Here, first stage, second stage, you get the output, but later on, the same thing is getting reduced. So, but here you can see that preservation of gradient information happens. The information what is found here is going here in the output. So, this is what you call it as gradient information preservation. That's what I told them. Memory is going to help us in this. So this is the exporting and gradient training in neural network. Okay, same as your, all these are same as your backpropagation neural network, forward pass, backward pass, bidirectional pass. All these are same as your normal neural network. This example I wanted to show you specifically. I have told you that what is the meaning of vanishing gradient and preserving the gradient with LSTM. LSTM has memory, remember that. Because of the memory, it is storing the gradient values. And you know, like the other GRU, it doesn't have the memory, but still, you know, because of the reset gates that are present there, it is going to correspondingly work, but with a better speed. See, what is this GRU about? With one example, it is explained here. See, a simple sport is a sequence of events. Real time, if you take any sports activity, can be considered as a sequence of events. And similarly, when we are speaking, that also, you know, with the time it is going to vary. So RNN in sports, you know, applying for basketball trajectories, they have taken an example, and also for classification in soccer videos, they have taken an example and they have designed that. This is GRU, which we have already discussed. See, these two units are gaining high importance because of you know, any time series problem we are analyzing, we are able to model it very easily because of these two. This is slightly higher cost because memory is present here, but here you can see that you just have the gates, reset gate, and whether you are going to reset it or just pass it on. One example they have given in TensorFlow website, I have just taken it. Actually, the idea is recurrent neural network, how it is used to the main application they are finding in RNN is, you know, whenever we are writing something, you know, whatever words that is supposed to come after that, whatever letters, characters that is that is supposed to follow that, we are able to get all these word embedding from the feed dictionary. They are taking the content and it is presented. We have seen it. See, some other examples for implementing this RNN in TensorFlow are, you know, like the task is to let the robot learn the behavior and follow the human instructions. The result would be, all these things are possible with recurrent neural network only. So time dependent, all these are time dependent. You give instruction and you do it after in a timely way. See here, a task is given. Sit down on the couch and watch TV. When you are done watching television, turn it off, put the pen on the table, toast some bread. All the sequence of instructions, all these can be executed with the help of recurrent network in TensorFlow. This is a demo result that is available, what I have taken from this website. Some more examples we can see. See here, this is another very clean, very easy example to understand our RNN. See here, whenever we have numerical values like this, we say that it is easy to model, etc. Similarly, whenever we have categorical values like this, grade A apple, grade B apple, grade C, grade D apples, we do classification problem very easily. Now, whenever we have a sentence like this, how do we handle it? How does machine learning handle it? A cat sat on the mat. How do you handle it? This is something, whenever text is dealt with, how do we handle it? You can have a linear model with SVM. So structure is going to be very important. We will see that we were using, in fact, SVM is also very good. For a sentimental analysis, we can use RNN also. We are using SVM also, which is found to be very efficient. See here, how to deal with this structure. You have a text, create a model using RNN, and then you analyze it. How text to be dealt with is very important. See here, we use RNN and SVM together also in many places for dealing with text. See here, you have a text. What is here will be your RNN. Then you have a linear model, which can be SVM. See how RNN works. See here. These are all single units. The cat sat on the mat. You are having projections and activities that is happening here. Hidden to hidden and input to hidden layer. See here. How this sequence can be learned by our machine and represented. This representation will become very easy in the case of our recurrent neural network because of the sequence. See here, you have memory here, you have activities, all these things passed on. We can see that, how it is passed on. You have an input layer, you have projections that is going out, how you are knowing the activities. So from text, normal text to RNN input, these are the steps that are followed, and we are easily dealing with this in machine learning. We are basically stacking them from hidden to the output layer. We are stacking them. This RNN was always found to be very unstable. In the initial stages, it was found to be very unstable. The reason being all these gating units, gradient clipping in case of overexplosion, gates initialization, all these became, and whenever you have a big data set, as I told, 1000 means you have to have 1000 layers like that. The initial problems were there in a created a lot of problems, and instability was there. And so simple neural network, we can very well see that for handling simple things, it is okay. Whenever it is going, the thing is going to increase, you will be dealing with a lot of layers. This was the biggest disadvantage I told. Similarly, whenever we have a huge data set, today we are easily moving into deep learning completely. In fact, there are a lot of correlation between this deep learning and our RNN. The reason being, number of hidden layer. You don't have one hidden layer. You have many hidden layer, depending on the problem we are taking. See here for sequence analysis also, whenever we have sequence analysis of longer sequences, uh, RNN works fine compared to other neural networks. Simple RNN works fine compared to other neural networks. So that becomes a very good advantage. So this gated recurrent neural networks, as I told you already, it was LSTM and GRU, they have their own applications. GRU is mainly used in mission translation and speech recognition tasks, where you don't need a lot of memory, like in the case of LSTM. Lot of variants have come with the time. We can see the how usages are there. They are both equally good. You can see that training loss and plot of training loss and weight updates, both are performing equally good. Exploding gradient problem, it was a major problem in traditional RNNs, and which makes them very hard to train. See here, you have exploding gradients there. So how to, in this paper by these persons in 2012 proposed a method for clipping the norm of the gradient and optimize the results. So many methods were proposed, and this method is still used now. Similarly, we had this initialization problem with the matrices, which is solved by the researchers. So you have to, one example of 2D moon data set was taken, and how optimization was done here. So these are all these things I have taken from the net for showing you. Sentiment analysis, predicting the sentiment and how it is useful. And whenever you have huge data sets, for training it, and the model is linear also, RNN is found to perform okay. But whenever, purely linear model, RNN takes lot of time, and compared to regression models and all, this is not that much efficient. For non-linear thing, it is very giving much better results. And whenever training, number of training data sets are more, this is found to be giving better results. See, like some examples, where our linear model was found to, this RNN was found to outperform the linear model. We can see that RNN takes 5 days on a single core CPU. So that is why we are going in for this NVIDIA's GPUs for speeding up our process of whatever it is, classification or class, whatever it is, or prediction. So visualizing the representation of words learned, individual words representing the average sentiment of the people, positive, negative sentiments. So this is the analysis. You have separate negative and positive words, and we see that the model is able to understand that easily. So, so this RNN is found to help much in predicting the test data in a easier manner. So RNN even though not much used like our backpropagation network, it is a competitive tool for text analysis. For large sample data set, it will be very useful. And GPU, if you have, the speed will become higher. The main problem, as I told, you have to have memory, LSTM or GRU. LSTM, if you are using, you definitely need lot of memory. So these trade-offs has to be taken care that the speed is somehow increased with the help of NVIDIA's GPU. Compared to linear model, the speed, complexity, and poor generalization with a small data set becomes very difficult with this RNN. So if GPU is used, then they find that speed is increased, complexity become less, and even for small data set, it is working okay compared to the linear models. So, we have to take care that we have higher processing capability whenever we are going to have RNN working with us, whether for sentimental analysis or for other applications where, RNN is found to be very effective. So this is what I have taken the basics of RNN, the main two LSTM and the GRU, and we have seen some applications. Next, as I was telling, the deep learning has come maybe in past 10 years or so. And it has, conquered most of the area where neural networks were used whenever we need higher accuracy in prediction or classification. Similarly for results in clip from Hinton et al. In 2012 paper, where he talks about speech recognition, image classification, accuracy metrics. So all these things, they found that deep learning was found to be much better. This deep learning has its roots way back from our RNN itself. We try to have many hidden layers. Even though we talk about sequence, because of the time series, what exactly happens in our deep learning is in hidden layer, you have not only one hidden layer, we have many. That is the reason it is found to work much better than other methods whenever we talk of image or speech recognition and some important types of data, like our satellite data, etc. So this deep learning is nothing but it differs from the neural network in only one way. It has several nodes between the input and output. Usually, when I started today, I talked neural network, one input layer, one output layer, and you have a black box. When this black box has only one layer of nodes, it is a simple neural network, which was found to be working fine. But when you have complicated nonlinear problems, this will not work out. You should have several layers of nodes between the input and output layers. And, where this hidden layer have series. The reason being, lot of work has to be done. For example, you will be doing feature identification, and some series of stages will be there between the input and output. So all these series of stages we can have in the hidden layer. So that is what is deep learning. So we can obviously see some correlation there now. So see here, you have input layer, output layer, and you have one hidden layer. Here you are having yeah, obviously only one input and one output layer will be there, but this hidden layer can be increased depending on the operation what we are going to do. When we are doing lot of operation like pre-processing, feature extraction, classification, everything we are going to do, you have to have many hidden layers. So obviously the working this deep learning needs fast processing. So you have to have GPU card in your machine, so that speed increases the speed. Otherwise, we'll be sitting in front of our machines. Actually, unsupervised, we know the two types of neural network, unsupervised learning in neural networks. Unsupervised, supervised, where we have supervised, you have a proper clear-cut input and output, whereas in unsupervised, the computer itself learns. So in deep learning, you know, this unsupervised feature learning was found to work very well. See here, you have f of x. So this is the input values, and this is the weights that is given here. The total will be, x will be this. I think this is a normal neural network, so you are able to understand it. X will be this value, whatever multiplication of all these, and this is a summation, and you get this. So you have a data set with fields and a classification. So all these are representing the attributes. So you feed in with one layer, this will work out fine. So training the neural network, you know, what we normally do is we initialize with random weights. Then we present a training pattern to it. Obviously, you have 3 input. So first instance, present a training pattern for that. Then you feed it and get the output. So you have this weight, multiplication, summation, all these things happens, and you get the output. The target output we compare. If it is going to be 0, we find that the error is higher. So we try to, you know, this will be removed, and we try to compare and then adjust weight based on the error. We have an error of 0.8 because the supposed value is 0, but we are getting 0.8 feedback. So next you take, you adjust. Next you take the next training pattern, you get 0.9, but the class you have indicated here is 1. So, you know, error is minus 0.1, and you know, this error we back propagate it and try to reduce. This is what we do in our normal neural network. Repeat this thousands of times, and you know, each time random training instance, and we make a slight weight adjustment, and algorithm for weight adjustment is there to reduce the error. So this is what happens. Similarly, decision, you see here, this is what simple decision boundary where you have items spread in this way. These are all belong to one category, and these belong to another category. So you have initial random weight. It can never, you cannot put a linear line and say it can be adjusted. So present a training instant and adjust the weight. So you adjust the weight. So when you adjust the weight to the neural network, slowly changes. See here, it has to come like this. It has to come like this. So slowly we are adjusting the weight. See here, now we get a decision boundary which is clearly This is a non-linear boundary, but we are able to clearly cover our items or the samples that are present in the decision boundary properly. So whenever you give weight and your algorithm, as far as here you are giving multiplying, do some operation and taking in the output. Error we find and then we give a result. But the real fact is these weight learning algorithms for neural network has to be very effective. For making small tiny adjustment, they take a lot of time and we try to have back propagation and again and try to fit the or map the input with the output. Now exactly what happens is you do a lot of work here. But when you can very well see that it is a tedious process, very tedious process. Mapping the input with the output is becoming a tedious process, because whenever we have a huge amount of data to be trained, we have input out large amount of input and output samples to be trained, then obviously it becomes very difficult to do this. This is working fine, but in real-time applications with huge amount of data, we have to look into that. We have to look into better algorithms where we find your CNN convolution neural network also is found to be good. Deep neural networks we are using because it is able to do lot of things together. See here we can see some other if you think that you have a linear function only, this we can never separate. So you should have many layers in the hidden layer, only then it will be able to separate. So use non-linear function, do complex boundary. You have to make it so that your data remains unchanged. So here, see here. So neural network use these boundaries. See here, SVM. What we try to do is we try to, because we are having multiple planes, they take one separate plane, and this becomes easier. That is why in many applications we find SVM more effective. Similarly, when we take examples of feature detection, where we are taking handwritten digits from postal envelope and all, we see that you have feature detectors here. See here, input and output we are taking. See, we try to each unit, what it tries to do is it understands the positive weight, negative weight, and how many you see what it can understand is horizontal line, vertical line. When there is a round, all these things it can easily recognize. So for each one it takes for strong signal, here it takes this place. Similarly, for training, this will be easy, vertical. So this is understood as 0. This is similarly when you have this and line together, it can understand it to be 9. So one horizontal line and this vertical line, this way it understand that this is 4 or this is 5 or this is 6. So features it is learning, and then see here, handwritten digit from postal envelopes. This is how it understands. The machine itself learns that. So these are all vertical lines. So how to classify it? So these are all horizontal lines. So small circles. So this is how it is able to understand the different horizontal line, vertical line, zeros. So whatever patterns we are giving, the unit will detect the corresponding shape. So main thing is having multiple layers will make sense. If you have only one layer, the performance may not be so good except for some applications. So what we try to do is multiple layers have been introduced in deep neural networks, and we are able to have better outputs. Basically, multiple layers, our brain also works like that only. Our brain, normal brain works in that way only. We have multiple layers of hidden thing, and they are able to generalize very well, and we are able to get better results. Our learning algorithms does not, see here, so many examples. It does not work well on multi-layer architectures, but with the deep learning, we are able to get good results. See here, let us imagine we try to do some pre-processing, then do some sequence of works. When we have multiple layers like this, it becomes very easy for us to do this map. Basically, we do the mapping between the input and output, and we say that it is training because we are going to give similar inputs during testing, and we check up whether we are able to get the results correspondingly. See here, multiple neural network. See here, what is happening is input layer, and this is the first of the hidden layer. First layer of the hidden layer. So first train these two, then these two layers are trained, then these two layers are trained, then these two layers are trained. We find that then these two, obviously from the input to the output, we have trained adjacent layer, and we get the output. We can see some similarity with recurrent neural networks. The present state depends on the previous state. That is what it is. So each of the layers are trained separately, and this you call it as auto. Whenever we are not dealing with non-output layer, we call it as auto encoder. So this auto encoder basically learns good features from the previous layer. See, this layer learns from this previous layer. This layer learns from this previous layer, because the input for this layer are coming through this only. You call this as auto encoder. So training this auto encoder helps in solving this weight adjustment problems. This is like problems what we encounter in normal neural network. Reproduce the input that is solved here with the help of the auto encoders. Similarly, whenever the layer that is connected to the output, you call it as decoder, because here you are going to see the output. So these are all very much connected to each other, and these are all called as auto encoders. And the last layer predicts from the previous. We should not always imagine there is only one output. Whenever there is classification problem and all, we'll be having more than one output. And for example, presence of disease or analyzing the type of disease, we will be having many output in the output layer, many nodes in the output layer. There are many types of deep learning that has come. You have many type of auto encoders that are available. We can very well see that now. What is the difference between normal neural network and this deep neural network is lot of layers in the hidden layer, which enhances the output. Many problems what we encounter in normal neural network is not found here, because we do lot of analysis here. The main thing, we encounter here is deep neural network, we need higher configuration if we are going to increase the number of hidden layers, and this NVIDIA's online GPUs are also available, which is helping us to do our research in deep learning. So, slowly we may be moving into the arena of deep learning, where everywhere we may be using this. Now we are able to get good accuracy and classification, accuracy for the network we are modeling. Next is, what are the avenues of research and what are the common applications we have in AI? See, this AI came into existence long back. We know that. AI is nothing but making the system work like a human being. Where we are putting artificial intelligence on the machines. This machine learning came after that. Machine learning is nothing but a subset of this AI, where machine is able to learn things and act accordingly. Slowly, this with this so many neural networks, we have moved into this deep learning now, where again it is a subset of this machine learning only. So we can very well see that AI is the parent of everything. Inside that you have this ML. Inside that you have deep learning. So lot of application areas are there. In solving problems in production system, expert system, common application areas of AI, I am listing out. You have computer perception, similarly searching and matching, similarly in natural language parsing, we are having AI application. Now AI is solving many types of problem very easily. What we have to do is, you have agent technology, multi-agent system. Now there you have to program in such a way that you define the problem very precisely, analyze the problem, and then you try to solve the problem. And whenever, say for example, you wanted to use robots for picking and placing, you first analyze and then program correspondingly, and then you will get the result. We are now using robots for many applications. Obviously, AI-based robots in countries like Japan and all. We are using robots for plucking mangoes, where you have image processing system with the sensors. It captures the image of the mangoes, then check up whether it is ripened to the extent it needs, and then it plucks it and gives it to the owner. So this AI-based technology is very helpful for real-time applications also. Similarly, pick and place robots are there for carrying huge loads. Similarly, now we can see that in bigger buildings and all, it is very difficult to clean because you have glass are there. Glasses has to be cleaned outside. It becomes very difficult for the human being to go and clean it. You have robots which are doing the work now, even in India. You can see that. Next is some another application area which is of very use for manufacturing is production system. You give some set of rules, and from that what operation to be performed. You have a control strategy which gives order for the rules that has to be done. Similarly, these are all you can have databases. We are finding out from which place water availability is there. So you take some parameters related to that soil, etc., etc. How much air contains humidity. All these things you take and analyze. So these problems are there. Similarly, finding water, where the water is. Similarly, design of VLSI systems, we have a lot of AI application, location of faults in computers and communication. Similarly, for medical diagnosis, we are using AI. Software development, we are using. Similarly, for space planning and exploration, that is, we are sending people to Mars, finding whether they can live there. All these things needs AI. We cannot send a huge population there to die. So many things are there. Using AI, we are able to do. Similarly, teaching the students to do specified tasks and identification of chemical compounds, all these. Similarly, forecasting how much damage has been done to the crops due to floods. All these applications, you need AI. Some of the production system languages, it was, all these are old languages. And similarly, expert systems can be developed to solve a lot of problems. Like what conclusion a doctor has to make based on the information he has. All these, you have a lot of expert system available, which makes inference, which happens to be a computer-aided accessory for a medical professional. So expert systems are increasing every day. So knowledge representation can be, like knowledge, we know it is a collection of facts, inference rule for a specific task, and procedural and declarative knowledges are there. Schemes that can be used are logical, semantic, conceptual, scripts, frames, etc. And so for representing knowledge, how we represent it. Here, rabbit is a rodent. Rodent is a mammal. Mammal eats food and has teeth. Here. So, eats food. Rabbit, it is a rodent. It is a mammal. It eats food and has teeth. So this is how we represent the knowledge. For knowledge representation in AI, we have a lot of methods. Similarly, for computers perception also, we are using AI for recognizing speech, where program can communicate directly with the machine and then act accordingly for interchanging information between the user and the human-machine interface. That's what I'm trying to call. Similarly, human communication involves spoken language, and it is easier to communicate. Similarly, for vision recognition, something is flying. Vision recognition, we can have AI. There are several categories of speech. Representative, where you make a speech depending on the state of proposition. You are stating something. Directive, we are giving commands. Similarly, commissive, we give a promise. Expressive, where we say thanks or apologize. Declarative, where so many types are there. So we can understand these types by using AI easily. By analyzing the voice itself, we can understand this. Similarly, there are a lot of algorithms for searching and matching, like breadth first search, depth first search. We can integrate it with our AI-based system and apply it in real-time application, like water jet problem. All these things we would have used, games, etc. So natural language processing, whenever we need a sentence, program transforms a sentence into data structure, and we parse it, and two types of parsing we are all aware of. So this is the top-down parsing. You have a sentence here, top-down parsing, and this is a bottom-up parsing. AI can easily understand that, what we are trying to mean. Similarly, banks use AI system to organize operation, invest in stocks, etc. Loan investigation, how it happened, all these can be done easily with the help of AI. Similarly, robots are able to perform better than humans in financial trading competitions and all. In hospitals and medicine also, AI is found to perform much better, and like for in the field of cardiology, neurology, embryology and all, lot of applications of AI is found. Similarly, obviously, whenever we are getting opportunity to work in some problems, we'll be able to solve some of the lacunas that are there. Similarly, in heavy industry maintenance, wherever you have robots, in Kalpakam atomic reactor, we cannot go to the place where we are having our important main reactor we cannot go, so robots are doing that. So telecommunication maintenance also we are using our AI only. Similarly, in games we can you see all our children's using AI based games. They are playing with a computer. Similarly, music and for antivirus detection and all, we are using AI. Similarly, we have a lot of advantages of using AI, and similarly, whenever we are having advantages, definitely we'll have disadvantages also. So this growth of AI in this century is growing like anything, and everywhere we are seeing that a lot of practical applications are found with our smartphones, right, with what is there in our hand. We are able to do everything, and main advantage they have is they don't sleep or have a break like humans, and they function for all 24 hours, which humans cannot do. Main disadvantage is AI cost is very high, and they are in many decision making problems. We can say that our brain is more much better than the normal than the robot. In fact, our analyzing cognitive capability is much more than the robots. So, and this is all I would like to share with you today. Thank you very much for listening. Any questions?
Any queries from the participant side? Okay, there are no queries. Yeah, thank you, madam.
Thank you.
Yeah, thank you for that wonderful thought-provoking lecture on training recurrent neural networks. You explained clearly about the LSTM and GRU, which is used for neural networks, and the need for neural networks, how the problems can be solved using the neural networks. And you gave what is the importance of deep learning and the common application areas in artificial intelligence. Thank you, ma'am, for clearly explaining all the topics with real-time examples. It was very informative. I hope the session was useful to all the participants as well. And a special thanks to you, madam, for kindly accepting our last-minute request to present this session. Thank you so much, ma'am.
Thank you, ma'am. It is a pleasure. It's a pleasure. Thank you.
Thank you very much, ma'am.
Thank you. Thank
On
you.
behalf of the Department of Computer Science and Engineering, we present this digital certificate to you, ma'am.
Yes.
Thank you, ma'am.
Thank you. Thank you. Thank you.
And the feedback link for today's session has been posted in the chat box. It will be open for the next 15 minutes. So dear participants, kindly fill the feedback form